So we started out the lecture talking about prediction, we're going to talk about regression, and then we kind of went and talked about association and correlation. What does this have to do with regression? Well, it turns out it has a lot to do with regression. So let's take a look at our parent height data set. So I have parent height, or their mid-parent height, and the child heights, and I've converted them to standard units. Okay, so here's the data set: mid-parent heights in standard units, child heights in standard units. Let's compute the correlation coefficient between these two. What do we expect it to be before we start? So positive, negative. If we think back to that scatter plot, remember, as you increase the mid-parent height, the child height also tends to increase. But it isn't like knowing the mid-parent height tells us exactly what the child height will be. So I'm expecting a correlation coefficient that's positive, but is it going to be close to 1 or closer to 0? I think it'll be closer to 0 than to 1. So yeah, here it is, 0.32. That tells us we have what you might call a weak positive relationship. This is a correlation coefficient that's closer to 0 than it is to 1. Okay, so let's take a look at our scatter plot again, complete with predictions. So I have the mid-parent height, the prediction here, and we saw that we have this line here. It's a straight line that captures the fact that as I increase the mid-parent height, the child height also increases. The question is, what's the slope of that line? Turns out it has something to do with correlation. So if I convert all of my data to standard units, and then I plot the line that has the slope of r, the correlation coefficient, I'm going to get the same thing. If I kind of go back and forth here, they look really pretty similar. Okay, so the slope of this line here, to recap, I've converted all of my data to standard units, as you'll notice here on the axes. I've plotted this line, not by doing the average of the neighbors kind of thing. I've plotted a straight line with slope equal to the correlation coefficient. And the intercept, well, the intercept is determined because this line is going to go through the point 0, 0. It's going to go through the origin. So it turns out that this correlation coefficient, which captures how associated two variables are, can be used for prediction, can be used for regression. This line, this yellow or this golden line here, is what we call the regression line. It's a line through the origin with slope equal to the correlation coefficient. If I have two attributes whose association is linear, okay, so like we kind of have here, this kind of looks like a linear relationship. In other words, the child height is some linear function of the mid-parent height. Then the graph of averages that we made before, this thing here, it's the average of all of the data within a small window of mid-parent height. Then if the association is linear, those two graphs will be pretty much the same. The graph of averages is approximately the regression line. So if we adopt this form that you probably used in high school for a straight line, mx plus b, then the prediction for a given input x, in other words, you tell me a mid-parent height and I want to know what the height of their child will be, well then to predict their height, I'm going to evaluate the function f of x. So for instance, suppose you tell me that a certain parent's height is, or a pair of parents, their mid-parent height is 1.5 in standard units. Well, then I go here, I find 1.5, I go up to the gold line, and I figure out what height that is. It's about 0.5. So my prediction is that the child height will be 0.5 standard units above the mean. So you might have heard the term regression to the mean. What that means is, if you have two parents who are very tall, their child is also likely to be tall, but not as tall as them. Their child will probably be closer to the mean. Still tall, still taller than average, but closer to the mean. And likewise, if you have two parents who are shorter, significantly shorter than average, and they have a child, that child is likely to be taller than them towards the mean. So we see this because the correlation coefficient isn't 1. Okay? If the correlation coefficient is 1, then the mid-parent height would be the child height, right? it would be easy. But since the correlation coefficient is less than 1, remember how I make my prediction. The intercept here, the y-intercept is 0. At x equals 0, y equals 0 for my gold line here. So to make a prediction for the child height, I take the mid-parent height and multiply by the correlation coefficient. Since the correlation coefficient is like 0.4, I'm always reducing the mid-parent height to come up with the child height. If the mid-parent height is 2, then I multiply it by 0.4. I get something like 0.8. Okay. If the mid-parent height is -2, then I get -0.8. Both of them are regressing towards the mean, towards 0. So that's what the phrase regression to the mean actually means. It means that things become less extreme over time. So this is just sort of repeating what I said on the previous slide. So let's take a step back now and say, well, what if my data, what if I want to work in the original units? So for example, these units, inches. Well, I can always make my prediction by converting the data to standard units and then converting my input. Say, okay, I want to predict the child height for a parent who is 1.5 standard deviations above the mean. Well, I could then convert, if I'm given the mid-parent height in inches, I could always convert that to standard units, make my prediction, then convert back. So that's kind of what we're saying here. If I'm, here. So my approach is I'm going to scale the mid-parent heights to standard units, compute the correlation coefficient, all in standard units, and then scale the predicted child height from standard units back to inches. So let's take the mean and standard deviation back in the original units now. So this Galton table here, look at this. I have everything in standard, or in original units, in inches. I'll convert each column to standard units, so I'm going to compute the mean, standard deviation of each column here. Okay. I already know the correlation coefficient. I've already computed it in standard units. It's 0.32. Okay. So what I do here is I'm going to take in an input which is not in standard units. It's in the original units. I'll convert it to standard units, multiply by the correlation coefficient to get the predicted child height in standard units. But then I need to convert that back to normal units. So to convert back to normal units, the inverse of subtracting the mean dividing by the standard deviation is multiplying the standard deviation and adding the mean. So this gives me a function that allows me to say, okay, suppose the parents are 56 inches tall. Their child is likely to be 58 inches tall. Suppose the parents were 70 inches tall in mid-parent height. Their child is likely to be 67 inches tall. So one thing to note here, by the way, maybe, is this a discussion question? Okay, I'll make this an impromptu discussion question. I plugged in 57 as the input, and then I got 58.9 as the output. I could make this an exam question, for instance. I could tell you nothing about the data. I could just say, okay, the mid-parent height is 57. Here's the output. Is 57 in standard units positive or negative? So think about it for a second. Is it positive or negative? So what's happened here, what I'm asking is 57 below average or above? And it has to be below average, because what I'm doing here is after I regress, after I plug this into my function, I'm getting a larger number. I'm regressing towards the mean. So if I started at 57 and went to 58.9, that means 57 had to be below average. Okay, so let's make our predictions now. So I'm going to predict using that function, this function here, predict with R. So what I'm doing is I'm just straight up taking the mid-parent height, dot apply, predict with R. I'm getting a new column called prediction R. And then I'm comparing it to that gold line that we got by doing the averaging. So this line here. Okay. So you'll take a look. They look pretty much identical, and that's no coincidence. Like I said before, if the pattern is linear, then they're pretty much the same thing. Okay, time for a discussion question. So a course has a midterm, its average is 70, its standard deviation is 10, and a really hard final exam. The average is 50, standard deviation is 12. So hopefully not this class, right? So if the scatter diagram or the scatter plot comparing the midterm and final scores for students looks linearly associated and it has a correlation coefficient of 0.75, then what's the predicted final exam score for a student who received a 90 on the midterm? Okay, so I'll let you calculate this for a second, and I'll let you pause, and we'll come back to it. All right, so the correlation coefficient here, 0.75, but to use the correlation coefficient to make my prediction, I first want to convert to standard units. Because remember, how I make a prediction is I take my input in standard units, multiply by the correlation coefficient, that's my prediction. Okay, so the input here is midterm score, and the student scored a 90. So that's in normal units. I need to convert that to standard units. Luckily, I was told that the average was a 70, the standard deviation was a 10. So I'm going to convert 90 to standard units. I'm going to do 90 minus 70 over 10. So that's 20 over 10 is 2. So their midterm score in standard units is 2. That means they were 2 standard deviations above the mean, which is very good. Okay, and then I need to come up with a prediction for their final exam score. So I take their input in standard units, which is 2, multiply by 0.75 or 3/4, so then I get 6 over 4 or 1.5 in standard units. So my prediction is they will have a final exam score of 1.5 in standard units. Now I need to convert that back to original units. Luckily, I'm told that the average here is a 50, the standard deviation was 12. So let's see, I said 1.5, so 1.5 times 12 is 18, and then I add 50 onto that, so that gives me 68, so C. Okay, so I did my math right. That's rare. So 68 points on the final exam is our prediction. Notice that they scored above average on the first exam, so we predict they're going to score above average on the second exam as well. So what does the regression line look like in original units? So here's our here's a formula which basically allows us to avoid going back to standard units. So I can just take an input in original units and apply the formula without having to go to standard units. Basically, the formula is converting for us. You know, what I'm doing here is I'm taking the input in normal units, in the original units, converting to standard units here, multiplying by the correlation coefficient, and then here I am converting back to normal units. So I'm saying here's my y in standard units. It equals r times x in standard units. Now I'm just going to solve for estimate of y here. And so what that gives us, if I just solve for this, you can you can come up with something like this. So there's a little bit of notation here. So I have in original units, this is the mean of the x's, the mean of the y's, standard deviation of the x's, standard deviation of the y's. I can solve for the original y in original units like this, and I get this. So this is a slightly more complicated formula, but what it's doing here is performing the regression by converting everything to standard units, multiplying by the correlation coefficient, then converting back. And so what you see here is that the slope is the standard deviation of the y's over the standard deviation of the x's times the correlation coefficient. It's not just correlation times x anymore. You have to apply this extra factor. The y-intercept is no longer going to pass through the origin. It'll be the average y minus this whole thing here. Okay. So you can remember this if you want. It'll be on cheat sheets exam for the exam or whatever. But you should know that there are two ways of computing the prediction, which are exactly the same. If I start in original units, I can either sort of manually go through the process of converting everything to standard units, then multiplying by the correlation coefficient. then converting back, or I can use this formula directly. Personally, I like the previous way. It's just a lot less for me to remember, although you end up remembering this formula because you see regression a bunch anyways. So again, the slope is given by correlation coefficient times this thing here. The y-intercept is the average of the y's minus the slope, m, times the average of the x's. So this m here is not the mean anymore. It was the mean on the previous slides, mx, my. This is the slope, m. So what you see is that the regression line looks the same in standard units as it does in original units. The only difference will be the scale of the x and y axes. Okay, so let's try to predict the retail price of a hybrid car with acceleration of 12.5. Okay, so we kind of know that as acceleration increases, price increases, but by how much? If I make a car which accelerates 1 kilometer per hour faster, 1 kilometer per hour per second faster, how much more expensive is it? Okay, so let's write some functions here. I will write one to compute the correlation. So I'm taking a table and then a column named x and a column named y. So then I'm going to convert x to standard units, y to standard units, take the mean. That gives me the correlation. The slope I compute by this formula here. So I'm not converting to standard units. I will take my table, the x column, the y column, but I won't convert to standard units. I will just multiply the correlation coefficient by the standard deviations, standard deviation of y over standard deviation of x. The intercept, again, I'm just going to use this formula here. And so I find the slope, I find the intercept, and then my prediction is m times the input plus the intercept. Slope times the input plus the intercept. And my prediction is $42,000, or euros, whatever units I was working in originally. Okay, so I could take a look at my data. I have plotted this line, which has slope m and intercept b, and here's the prediction for any given acceleration. I can plug it in and I get the predicted price. Now, the original question was, for each additional unit of acceleration, how does the price change? That's what the slope tells us. If I increase the x unit, if I increase the x variable by 1, how much does the y variable increase? And here I see it's $5,067. So making a car that accelerates 1 unit faster costs the buyer $5,000 more.